Welcome back. Welcome to the optical communication course. So we today we see few numericals again here. Now, next numerical is about to understand that how that refractive index is to be obtained there. Now, the velocity of light, the of light in the velocity of light in the fiber core of a step index fiber is as 2.01 into 10 to the power 8 meter per second. The critical angle of incidence, the critical angle of incidence, okay, the critical angle of incidence at the intersection of the fiber core at the at the intersection of the fiber core at the intersection of the fiber core and the cladding is 80 degree. Full stop. Estimate estimate the values of estimate the values of the numerical aperture. Estimate the values of the numerical aperture as well as the acceptance angle as well as the acceptance angle of of incident light rays for the for the optical fiber placed in air full stop. Assume that assume that the fiber assume that the fiber has a core diameter fiber has core diameter which is suitable to which is suitable to considered by which is suitable to considered by optical ray analysis optical ray analysis now now the statement is too big. If you see that here the value is given that velocity of light in the fiber core, okay, which fiber? That is about a step index fiber. Velocity of light in the fiber core of a step index fiber is given, and the critical angle of incidence of the core and cladding is given. So here the velocity is given. Velocity means what? Which velocity is here? So that is for the uh, to obtain the means Generally, we say that light is about velocity of light is about 3 into 10 to the power 8. Okay, velocity of light is nothing but a 3 into 10 to the power 8. But here, velocity of light in the fiber core. Okay, velocity of light in the fiber core means that is about a v is given. Okay, this is about a velocity of light in a fiber core, and that velocity is less than this light velocity. That velocity is less than the light velocity. Next, about a critical acceptance angle is given. It is about 80 degrees. That is nothing but a theta c. Then our aim is about to obtain the numerical aperture. That is a. Okay, we need to find out a numerical aperture here, as well as the acceptance angle of the cone. That is about a theta a. Here we need to find out a numerical aperture. Then a second, that is the acceptance angle of the incident light rays for the optical fiber. Okay, for the optical fiber placed in air. Okay, that is about air. That's why that is about a place in there. Place same. Here we need to say that a acceptance angle. Then we have a numerical aperture, that is about difference between the refractive index core and cladding here. Okay, and then assume that the fiber has a core diameter which is suitable to be considered by the optical ray analysis. Why it is mentioned? Because that fiber is given. Okay, this one, the fiber, it has a core and cladding. So means your light is when light launch inside the fiber. Okay, light launch inside the fiber. So then and then here that light and this fiber core, there is interaction between the core of fiber and this air. So that's why that is a acceptance angle here. Okay, that's why here is the acceptance angle. Now then it is mentioned in the numerical itself. Our aim is about to consider that assume that the fiber has a core, assume that the fiber has a core diameter which is suitable to be considered by the optical ray analysis. Means suitable to be considered means what? Whichever the core size is there, that will be sufficient. Okay, that will be sufficient to propagate the light. Okay, whichever the diameter of this particular fiber. Assume that the fiber core has a core diameter. Fiber has a core diameter which is suitable to consider by the optical ray analysis. Means light can be propagating through the fiber of fiber core here. So now we consider here the one obtain that whatever the numerical aperture. So before that, we'll see that what are the given terms. Now the given term here, first term is given, that is velocity, whichever the light is propagating through the core. So it is 2.01 into 10 to the power 8. And then a critical angle is given, that is about theta c is equal to 80 degree. Theta c is equal to 80 degree. Now the term is given. Okay, now we have the term given, that is about the v and theta c. Now and we need to find out the numerical aperture Na. Na is equal to what? N is equal to what? N1 square minus N2 square. That is fast. So now here, if you see that we doesn't have the values of N1, we doesn't have the values of N2. Next, we will see that a critical angle equation. That a critical angle. That critical angle is equal to what? Because the term is given for the critical angle. So sine inverse of what? Sine inverse of N2 by N1. Now even here we have the only one term. We doesn't have this two term. But from this, but from this velocity, okay, whatever the velocity of a core is given, core velocity, okay, whichever the light is propagating velocity of a light in the fiber core of a step index fiber is given here. So that's why here we have the core velocity of a light propagating through the core is about a 2.0. Now from that we can find out the refractive index of this core. So now how to find out the refractive index of a core? Generally we know that a velocity of a light propagating through the core is equal to what? C by N1. That c is nothing but what? Light velocity, and n1 is the refractive index of the core. But we have the term, we know that known term is v and c here. So we can find out the n1. N1 is equal to what? C by v. That is about what? 3 into 10 to the power 8 divided by the, what will be the v? V is equal to what? 2.01 into 10 to the power 8 meter per second. Both. Now after solving, we'll get the n1 is equal to 1.49. Means we have a one term here in the critical angle. If you put that a n1 value, that is about a 1.49. If you put that, if you put that n1 is equal to 1.49, then you will get the, what is the value of n2. Now we'll solve it here. So theta c, okay, now we can consider that theta c is equal to what? Here we can say that a critical angle, that is about 80 degrees given. So if you consider instead of sine inverse, you can consider that sine of theta c. Means likewise, sine of theta c is equal to what? N2 by n1. And theta c critical angle is about a 80 degree, sine of 80 degree divided by n2 by 1.49. Then by solving, you will get the n2. N2 value is what? After solving this, sine of 80 degree, some term we are getting, and from this we'll get that a n2 is equal to what? The 1.467. Okay, n2 is equal to 1.467. It is about to give. Now then, from this n1 and n2 we are getting. Now if you put that the values of a, if you put all the values here, then a numerical aperture is equal to what? Na is equal to what? Under root of n1 square minus n2 square. And then you will get that Na is equal to under root of what? A 1.49 square minus 1.467 square. And you will get the numerical aperture. Na is equal to 0.259. Okay, directly. If you solve that, you will get that n1 and n2 value. These are the n1, this one is the n2 value. If you put that n1 and n2 values, you will get the numerical aperture. Now, here it is asking about what? Estimate the values of numerical aperture. Now we obtain the numerical aperture value as well as the acceptance angle. Now what do you mean by the acceptance angle? Acceptance angle is what? That is about a theta A is equal to sine inverse of numerical aperture. Theta A is equal to sine inverse of numerical aperture. Now we know that numerical aperture here. Okay, numerical aperture we have obtained that Na is equal to 0.259. Na is equal to what? A 0.2959. And the acceptance angle is what? This one is the acceptance angle. Okay, this one is about a acceptance cone here. In a red here, we have marked about the acceptance. So that light is propagating, whichever the power light launch inside the power, inside the fiber here. Okay, this one is about a source. It can be LED or whichever the light rays coming here, that will be propagating through the fiber. So whichever the rays are accepted by the fiber, because of there is a difference in the refractive index of a core and a air. There is a difference in the refractive index of a core and the air here. Because from the source to the fiber, we need a coupler. So in between that fiber core and that fiber core and a source, there may be a coupler, and inside that particular core here, we say there is a medium of air. So whenever the light launches from this particular source to the fiber, so in that case, that light may be accepted by the fiber. So that's why we need to find out what will be the acceptance angle or a acceptance cone. This is about a acceptance cones of a fiber. So we can consider here that theta A is about the acceptance angle. That is theta is equal to sine inverse of Na. We'll get that a acceptance angle, that is the sine inverse of Na is what? A 0.259. And if you solve it, we'll get that acceptance angle, that is about the 15.01. Okay, 15.01 degree. Now that's all about your estimate the numerical aperture. Okay, estimate the numerical aperture, estimate the acceptance angle. We obtain that numerical aperture and acceptance angle. But here the terms are given, only these two terms are given. That is critical angle and the velocity of a light propagating through the fiber core. It is given. But light velocity is given, that is in a core. So that's why from the core, which light is propagating, so we can find out the refractive index from that. So we know that velocity of a light in a core, okay, velocity of a light in a core, it is depending upon that what will be the refractive index of a core. So that's why natural whatever the light speed here, and this one is about n1. So we'll get that an1 from this, and then from this critical angle equation we'll get the n2. Then similarly you can find out numerical aperture and then a acceptance angle of the fiber there. Okay, so that's about a here we need to obtain that a numerical aperture of a given particular fiber and all, and then we need to consider that what will be the another here another solution, another example will continue, find out that velocity of a light. Okay, so next numerical in a given optical fiber in a given in a given optical fiber. Okay, maybe I lost here. In a given optical fiber, the relative refractive index the relative refractive index difference between the core and cladding between the core and cladding is 0.9%, is 0.9%, and a solid and a solid acceptance angle and a solid acceptance angle in air is 0.15 radian. Okay, it is about a 0.15 radian. Determine determine the velocity of light determine the velocity of light in the fiber core in the fiber core assuming the fiber assuming the fiber okay, assuming the fiber has a core diameter has a core diameter such that such that ray theory can be applied for analysis. Now in this numerical, if you see that it is given that if here air that is about a solid acceptance angle in air that is about 0.15 radian. Okay, this one is about acceptance angle 1.5 0.15 radian. and that refractive index difference is about a zero point 0.9 is given. If it is a 1%, okay, we can say that then there will be a del will be a different value. But now consider that we have that equation given, and our aim is about to find out the determine the velocity of light in the fiber core. Means we need to find out here velocity of a light in a fiber core. That is equal to what? C by n1. Okay, this one is nothing but what? A velocity of light in core. Okay, or in a fiber core. And difference is given, that is about a 0.9%. If you see that it is about approximately 0.009, and a acceptance angle in a air, it is about a theta a is equal to given, that is about 0.15 radian. And if you find out in terms of a degree, okay, you can find out that 8.594 degree. Our aim is about to consider here what will be the velocity. We need to find out the what will be the velocity. So we for that we need to find out the what will be the n1 value. To obtain the n1 value, okay, to obtain the n1 value, we have the scope of what that to obtain the that n1 using this del. Okay, we need to find out the acceptance angle using the del. So to find out, we consider that a del is equal to what? A n1 square minus n2 square divided by twice of n1. Okay, now here that del is equal to what? N1 square minus n2 square divided by twice of n1. So that we'll get the value of a numerical aperture. But right now, if you see this particular equation, so we doesn't know the value of that even sorry twice of n1 square. We doesn't know the value of this even the n2 here. Okay, so because they have just given the equation, okay, they have just given the equation of what a theta a acceptance angle here. So from that we can calculate the this term. Okay, from this del we can calculate it, or we can use this particular term. So now how? Okay, we'll proceed now. Now another portion is given that is about the acceptance angle. So acceptance angle is given that is about a 8.59 degree. So theta a is equal to what? A sine inverse of numerical aperture. Okay, theta is equal to sine inverse of numerical. Means we can say that sine of theta a is equal to na is equal to under root of n1 square minus n2 square. So if you put the values of theta a here, we'll get that n1 and n2 term. Okay, if you put that a value of theta a here, you will get the value of a n1 and a n2. So after solving this sine of theta a, sine of theta a means what? Sine of 8.594 into under root of n1 square minus n2 square. After solving this, if you put that value, you will get that n1 square minus n2 square. Because you can take a under root of this one and you will get that n1 and n2. So you will get that n1 minus n2 square, that is something, okay, 0.0022 here. Now put that here, put these values here. So you will get that an1. Okay, after putting the values of n1 minus n2 square, you will get the value of a n1 there. So n1 is equal to what? Sorry, we need to write down a del here. So del is about a 0.009 is equal to whatever the values we are getting divided by twice of n1 square. After solving, you will get the value of a n1. And once we got the n1, okay, once we got the n1, that is about 1.115. Okay, so then you can put the values of v equal to c by n1, and v is equal to c by n1 is equal to 2.69 into 10 to the power 8 per second. Now we can check it, okay, whether this one n1 is about 1 point, okay, or whichever the figure I have written here, you need to verify, okay, using your calculator there. So after that, you'll get the. So simple. There are the two terms given in the numerical. You see that these two terms are given. That terms are what? A acceptance solid acceptance angle. Okay, solid acceptance angle is given, that is about 0.15, and another term is given, that is about a core and cladding. Okay, this one you can say that is about a the index difference of a core and cladding is given 0.09. Okay, 0.09, and then we need to find out a velocity of a light. So we need to find out the velocity of a light in a core. To find out the velocity of a light, we know the equation of velocity of light is equal to v is equal to c by n1. Then using that, we obtain the we need to obtain the v here. But before that, we need to find out n1. How to find out n1? The terms are given, that is about a del and this acceptance angle. Now we have written the equations of a del and the acceptance angle there. And from that, one is a common term, n1 square minus n2 square, that is about a common term is there. And that is to be used to obtain the n1. Once we have obtained the n1 value, we put the value of n1 here, then we can obtain the whatever the velocity propagating through the fiber core there. That is about it. Just like if you see that, it looks like some okay hectic, okay, but you can may proceed, okay, you may proceed by solving this. Now next one, okay, next numerical, consider a multimode silica fiber, multimode silica fiber that has that has a core, refractive index, core refractive index n1, okay, that n1 is equal to 1.480, okay, because I have written directly here, n1 is equal to 1.480, and a cladding index, that is n2 is equal to 1.460. Okay, n2 is equal to 1.460, n2 is n1 1.480. Difference of what? Zero point 0.2. Okay, 1.480, 1.460. Find, okay, now here we need to consider that, find a critical angle, find the critical angle, we just consider theta c here, find the critical angle theta c, then find the numerical aperture, that is NA, and the acceptance angle theta A. Now that is what? A critical angle. Okay, that is called as a critical angle. This one is called as a numerical aperture, and this one is called as a acceptance angle. Now our aim is about to find out a critical angle, numerical aperture, and a acceptance. So we know the all the equations for the critical angle there. Okay, angle, that equations for the critical angle, that is about a sine inverse of n2 by n1. Okay, sine inverse of what? N2 by n1. Or we can find out, okay, or you can find out the numerical aperture. Okay, likewise, because we have the given term that critical angle n2 by n1, and then the numerical aperture is equal to what? N2 square, sorry, n1 square minus. Okay, numerical aperture is what? N1 square minus n2 square. And a acceptance angle, that is theta a, is equal to sine inverse of na. That is a sine inverse of n1 square minus n2 square. So this one, if you put the values here, so now n1 is given 1.480, n2 is given 1.460. Okay, 1.480, and so we can say that sine inverse of what? 1.460 divided by 1.480 is equal to, if you solve it, you'll get the answer for 80.5 degree. Okay, 80.5 degree. And if you put the values here, n1 and n2, so you'll get that 0.242. And if you put that here, the values of a numerical aperture, okay, 2.242. So you'll get that acceptance angle will be of a 14 degree. Just like we should know that what is the term, and that term is used for what particular purpose to obtain the numerical apertures and all. And then we can calculate that value, or even if the equation, if you consider here, so we can calculate that even if the supposed to be any n1 or n2 is given, so we can relate that, and we can calculate the other values too. So will consider here the fact of what, how to obtain the values of critical angle, numerical aperture, and a acceptance angle there. Another one, consider a multimode fiber. Consider multimode fiber that has that has a co-refractive index, that has a co-refractive index of 1.480, and and core cladding difference, and a core cladding index difference. Okay, so index difference is of what? A 2.0%. Okay, 2.0%. Find find A, numerical aperture, then B, find A, numerical aperture, then B, acceptance angle, then C, critical angle. We know that numerical aperture is equal to what? Under root of what? N1 square minus n2 square. But we doesn't have the values of what? N2 right now. We have the N1 value, but we doesn't have the N2 value. So either we can use the another equations for this Na. Na is equal to what? N1 under root of a twice of del here. If you put this one, you will get the, okay. If you put that n1 into twice of del, you will get the numerical aperture. N1 is what? That N1 is equal to 1.480 and del is about 2%. 2% means what? 0.02. Okay, 0.02. And this one, okay, percent means del will be what? 2%. Okay, so del is what? It is about 2%. So 2% means what? Point of 2.0 is given. Okay, so 2.0. So 2% was 0.20. So you can put that 0.20 here value, and N1 is nothing but a 1.48 co-refracted 0.480. So you will get the value numerical aperture value, that is about a 0.296. Next, about a acceptance angle in the air, that is theta is equal to what? Sine inverse of numerical aperture. We obtain the numerical aperture value, that is 0.296. Put that 0.296 here, you will get that a theta A, that is about a 7.2 degree. Then a critical angle is equal to what? Sine inverse of what? N2 by N1. Now our aim is about to obtain the value of a N2 now. How to obtain the value of N2? To obtain the N2, we need to consider because the difference, we know that a cladding difference is there, so that's why N2 is equal to what? N1 into 1 minus del. N2 is equal to what? N1 into 1 minus del. Now what is the 1? The del here. N1 is what? We have the 1.480 and del 1.0.020. Then we'll get that N2. N2 after solving, that will be what? 1.450. Put that 1.450 here. So here a sine inverse of 1.450 divided by 1.480. Okay, 1.450 divided by 1.480. So you will get the answer for this critical angle, that is about a 78.5 degree. Okay, that is about a critical angle value. So directly, okay, we are getting the answer for this critical angle value. So that's why I'm saying we should know that, okay, what type of, okay, method we are using, okay, and what, for what purpose, what terms are given. So we just remember the formulation. You people are able to obtain the equations here. We'll proceed further. Next one, a step index fiber. A step index fiber has a normalized frequency, has normalized frequency V is equal to 26.6 at a 1300 nanometer 1300 nanometer wavelength, at a 1300 nanometer wavelength. Step index fiber has a normalized frequency V is equal to 26.6 at a 1300, okay, 1300 nanometer wavelength. If the core radius if the core radius is 25 micrometer, what is the what is the numerical aperture? What is the numerical aperture? Now the term is given, that is a normalized frequency or V number we say, okay, and that core radius is given. that core radius is given, and this one wavelength is given. Now then, to obtain the numerical aperture, Na is equal to what? Na is equal to V number, or normalized frequency we say that lambda by twice by A. Lambda by twice by A. So we'll put that V here value, that is the 26.6 into lambda. Lambda is equal to what? 1300 nanometer. Okay, that is about 10 to the power minus 9. And a core radius of, that is 2 pi, and a core radius of what? A 25 micrometer. So twice by A. A is nothing but what? This A is called as a core radius. And this is about a wavelength. And this one is about a normalized. Now 25 micrometer. 25 micrometer what? 10 to the power minus 6. Solve it. You will get the answer for this numerical aperture. That is about a point. Okay, you will get the answer for the numerical aperture. That is about a point 2. So now here this fiber, that is called as a strip index fiber, because the strip index fiber, it has a core diffractive index constant throughout the core here. Okay, strip index fiber in which refractive index of a core is a constant throughout this core radius or a core diameter. Okay, then we can say that here for a strip index fiber that normalized frequency is given and the wavelength is given, then core radius is given. For that we obtain here a numerical aperture.